So the Fibonacci numbers start with 0 and 1, and then each subsequent term is obtained from adding up the previous two terms. So it's described above. The generating function for this sequence is f of t summation from n equals 0 to infinity of fn t to the n. So last time we showed that this function satisfies the following equation: f of t equals t plus t times f of t plus t squared times f of t, which led us to determining the generating function as this rational function. So it's a ratio of two polynomials in t, t and 1 minus t squared. And this further led us to use the following two numbers. So we remember we denoted alpha 1 plus square root of 5 over 2 and beta 1 minus square root of 5 over 2 are the solutions of the quadratic x squared minus x minus 1 equals 0. And with these solutions in mind, we can expand the rational function as follows: as 1 over square root of 5, 1 minus t alpha, minus 1 over square root of 5, 1 minus t beta. And these led us to determine this formal power series, to rewrite it as 1 over square root of 5, alpha to the n, beta to the minus beta to the n, t to the n. So if we compare the formula we have here, where the coefficient of t to the n is the nth Fibonacci number, with the formula that we have here, we can deduce that the n Fibonacci number, fn, is going to equal 1 over square root of 5, alpha to the n minus beta to the n. Now, one can actually approximate this alpha. So alpha is about 1.618, and beta is about minus 0.618. And again, I leave it as an exercise for you to actually figure out from this formula that fn equals the floor of alpha to the n plus 1 over 2 divided by square root of 5, where here our notation is that floor of x is the largest integer that is less than or equal to x. So f of n behaves pretty much like alpha to the n divided by square root of 5. So it's going to have an exponential growth. So now let's do more examples which involve the notion of a generating function and formal power series. So let's go back to the previous topic, which involved weak compositions. The notation will be a little bit different from what we did before, but I hope that the underlying notions will be clear. So let's define this n with double brackets, choose k, is defined as the number of what I call k combinations with repetitions from a set with n elements. So to make our life easier, from our usual set n, which consists of all the integers from 1 to n. So essentially here, what we want to count, we basically choose k elements from this set n, and the order doesn't matter, so we disregard the order, but allowing repetitions. So recall that when we, for the usual notation of n choose k, which counted the number of k subsets, these are usually also called the number of k combinations without repetitions. And we had a formula in our previous, from our previous classes, this one and n factorial divided by k minus 1 times n minus k factorial. So here the big difference is that we allow repetition. So we can pick an element several times. Okay. So let's see how this works, and perhaps it's easier to just see an example first. So, example. So here, let's take the n equals 2. So our set, so 2 elements, 1 and 2. And because we can pick elements allowing repetition, we can pick as many elements as we want. We can even pick 3 elements. So let's say k equals 3. So what in the world would be this number? 2, choose 3. The number of 3 combinations with repetitions from a set with 2 elements. So what could we possibly pick? Well, we could pick, so let's list them here. We could pick 1. Can pick 1 3 times. Okay, so that's one choice. We can pick 1 twice and 2 the last time. And then we can pick 1 once, and we can pick 2 twice. And then we can pick 2 3 times. So I think these are all possibilities. If we pick, again, because the order doesn't matter, this is considered to be the same thing as 1 2 1, which is the same thing as 2 1 1. And similarly here, 1 2 2 would be the same thing as 2 1 2, would be the same thing as 2 2 1. Okay, so in this case, it seems like this number is 4. But what's the number of it in general? So let's do a couple of approaches for this problem. So again, we have that the parameter that we're interested counts something. Now let's figure out what it counts. So we're picking n elements. We're picking k elements from a set with n elements. So let's say we have our elements 1, 2, all the way up to n here. So let's say the element 1, it gets picked a1 times, the element 2 gets picked a2 times, the element n gets picked an times. And what property do these numbers have? Well, these numbers a1, a2, an have to be greater or equal to 0. And since we're picking k elements in total, it means that the sum of these elements, a1 plus an, must equal k. So from the definitions, it follows that this parameter, let me erase here and put it maybe, result that this parameter equals the number of n tuples a1 an, such that a1 plus blah blah plus an equals k, and a1 a2 an is greater or equal to 0. So this is a little bit different than the notation that we used in the previous lecture, where I think n and k were switched. So just pay attention to that. But the result should be clear, and the idea should be clear that these two quantities, the left and the right, are the same. And now this is the same thing as, so n is the number of weak compositions of k as an n-ordered double. And we had a formula in the previous lecture. It was n plus k minus 1. Choose n minus 1. If you forget the formula for this problem, as it can happen, one way to remember it here is the following. You can think about when we're counting the solutions a1 plus a2 plus blah 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 plus an equals k. So think about the A1 as being a set of A1 dots. So this is A1. And then the plus between them is a different symbol, is a plus. And then A2, you have A2 dots. And then you have a plus between it, and so on. Plus, the last one is AN, which you have AN dots. Now in my picture, all of these numbers, A1, A2, AN, are greater or equal to 0, but they may be, some of them may be 0. So for example, in the situation before where we had n equals 2, and we're picking an element 3 times, and we picked the element 1, 1, 1 3 times, our equation corresponding to that would be A1 is 3 plus A2 is 0 equals 3. That would be our equation, and the arrangement would be 3 dots, a plus. Yeah. Okay. So similarly, if I had the next one, 1, 1, 2, that corresponded to the equation 2 plus 1, and that can be represented by 2 dots, a plus, and another dot. 1, 1, 2 would give me, oh no, it's the same one. 1, 2, 2 will give me 1 plus 2, which is 1 dot plus 2 dots. And then 2, 2, 2 will give me 0 plus 3, which is a plus is at the beginning, and then you have 3's. So now, if you pay attention here for this these arrangements, you see what do we have? Well, we have exactly 1 plus, and it's essentially the number of ways of choosing a plus, putting a plus in this set with four elements. So here the answer is essentially 4 choose 1, or 4, it's the same thing as 4 choose 3, which is 4. So coming back to our general equation, trying to count the number of solutions of this equation, A1 plus AN equals K, with all the numbers non greater or equal to 0. Overall here, in total, we have, how many pluses we have? We have K minus 1 pluses. And how many dots? Well, the number of dots is the sum of the numbers A1 plus A2 plus AN. Well, yeah, I have made a mistake. So the number of pluses is N minus 1, and the number of dots is K. And so any solution of our equation, any solution of this equation, corresponds to choosing N minus 1 positions where the pluses are among these N minus 1 plus K symbols. So the number of solutions is going to be N minus 1 plus K, choose N minus 1, which is the same thing as N minus 1 plus K, choose K. Okay, so this is the one here. All right, so let's have another approach to this problem. So let's look at it in a different way. So let's try to look at it using generating functions. So with generating functions. So let's say again, we have our elements 1, 2, n, and for each of them, let's say we have some variable t1, t2, tn, and let's look at the following product of formal power series. So let's look at 1 plus t1 squared. So this would correspond pretty much to the element 1 in some sense, 1 plus t2 squared, and all the way to 1 plus tn squared. Now, this is a product of n formal power series, and you can evaluate it using the rules for the product. And what do you get in the result? You're going to get something of the form summation. So from the first sum, you pick t1 to some power, let's say e1, maybe, yeah, let's call it A1. T1, you're gonna pick T1 to the power A1. From the second one, you're gonna pick T2 to the power A2, and so on, Tn to the power An. And what properties do these numbers have? It's just that they're greater or equal to 0. So when you evaluate, you're gonna have a sum of these monomials, which involve T1, T2, Tn. But now let's see what happens if we set all these variables T1, blah, blah, Tn equals T. Okay. Then what am I going to have at the beginning? I'm just going to have 1 plus t squared, this kind of geometric formal power series, multiplied by itself n times. And it is going to equal what? A summation over a1, an greater or equal to 0 of, now, t is everywhere. It's the same as t1, the same as t2, it's the same as tn. So it's going to be t to the power a1 plus a2 plus blah, 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 plus an. But now, if we group the terms with the same exponent together, we can write this as a summation over k greater from 0 to infinity, t to the k. And what is going to be the coefficient of t to the k? Well, t to the k, the coefficient, is going to be the number of times we're going to have some n-tuple a1, a2, an, whose sum is going to equal k. And we just saw on the previous page that that number of times is going to be this double choose k. And so this parameter, the number of k combinations of repetition from a set with n elements. Okay, so this gives us, so we have here again, n is considered to be fixed. You can pick any number you want, a natural number. And then we saw that it doesn't matter, k doesn't have to be less than or equal to n when we're taking combinations with repetition. So k can be anything from 0 to infinity. And so this formula here holds for every n. So we're gonna have n factors here. Okay. Now, can this formula actually help us to maybe get a new expression for this parameter? Well, let's write it again on the next page in a different way. Okay, so we had that 1 plus t squared n times, so I'm just going to put it to power n, equals summation for k equals 0 to infinity of this parameter times t to the k. But now we remember that 1 plus t squared is this geometric form of power series. This equals 1 over 1 minus t, and it's the same thing as 1 minus t to the power minus 1. So from these two relations, what we get is that 1 minus t to the power minus n, so let me put it in red so we remember it. We're going to get 1 minus t to the power minus n. It's going to be the summation for k 0 to infinity t to the k. Okay, so the right-hand side, there's not much more we can do there. But on the left-hand side, we can use the binomial formula. And the binomial formula, when you have the exponent that is negative in this case, is going to be an infinite series. And it's the infinite, this formal power series, summation from k equals 0 to infinity, minus n choose k. And over here, I'm going to have minus t to the k. And if you expand this, if you rewrite it, actually, it's a summation from k equals 0 to infinity of minus n choose k times minus 1 to the k times t to the k. Now, if you combine these two formulas, the one in red and the one in blue, they lead to the fact that the number of k combinations from a set of 10 elements with repetition is going to equal minus 1 to the k minus n choose k. Now, this looks kind of strange. What is this number? Well, we can calculate it. Minus 1 to the k minus n, choose k. It's going to be minus 1 to the k. And here we have k factorial at the denominator, and we go minus n times minus n minus 1. We have to have k factors at the top, so it's going to be minus n minus k plus 1. And now, here's what we're going to do. On the top, we have k factors here, and each of them is a negative of something. So we're going to write each of them as minus whatever the number is, and we're going to catch a minus 1 to the k from those k factors. And that minus 1 to the k is going to meet with the minus 1 over to the k from the front, and they're going to become a 1. And on the top, we're going to get n times n plus 1 all the way to n plus k minus 1. And this is the same if you write it from in the reverse order, from n plus k minus 1 going down all the way to n plus 1. And again, there are k factors there. It's n plus k minus 1, choose k, which is the same thing as n plus k minus 1, choose n. The formulas that we had on the previous page. Okay. All right, so that's another example of generating functions. Let's do another one, which is perhaps one of the most famous sequences. This involves what are called Catalan numbers. Now, Catalan numbers have been studied by many people, going back to Euler and various other mathematicians. There's a very beautiful book written by Richard Stanley, with an appendix by Igor Pak. So the appendix describes the history of these numbers. I think I read there that these numbers should have been called maybe Euler numbers or Euler-Segner numbers and so on. But anyway, it's a fascinating story how the numbers got to be called Catalan. Catalan was a mathematician, a Belgian mathematician who studied these numbers, but he wasn't the first one to do it. And in the book by Richard Stanley, I think there are 214 interpretations of these numbers. So don't be scared. We're not going to go through all of them. I don't know all of them. I know some. So let's start with the definition. So let's say we have an n-gon. So in my case, let's just do the pentagon. Now you can draw some diagonals inside the pentagon, and some of them are gonna intersect. So for example, if I draw these two diagonals, I call them intersecting because they cross somewhere inside. But you can draw some diagonals that do not intersect, like for example this one. And it's not too difficult to show that if you have an so let's try to sketch it here. If you have an n-gon in general, let's say you go from 1 to n, 3, and so on, n minus 1, you can draw n minus 3, there exist n minus 3 non-crossing diagonals. So the simplest ones to draw are the ones that all contain the same point, for example, like this. But there are many other ways to draw n minus 3 non-crossing diagonals. Okay, so here's the definition for the Catalan numbers. For n greater or equal to 1, Cn, the nth Catalan number, is the number of let's say decompositions of a regular n plus 2 gon by, so in this case, since we're using n plus 2, we can draw minus 3 diagonals by n minus 1 non-crossing diagonals. So there's a bit of a mismatch between Cn and the size of the regular polygon. But yeah, if we play with it a little bit, you'll get used to it. So let's do some simple examples and let's see what these values are. So perhaps the simplest one is I can do it here on the top. I have okay, n equals 1. When n equals 1, n plus 2 is 3. So we're looking at an equilateral triangle. In how many ways can we put 1 minus 1, so 0 non-crossing diagonals. So in this case, the triangle is a triangle, there's no diagonal, so we can say that the first Catalan number C1 is 1. Okay. Let's do the picture below here for what happens when n equals 2. So when n equals 2, let's see, we have a square, and we can triangulate with one diagonal this way, but there's another way that we can triangulate it. We can go this way. So this leads us to C2 equals 2. Okay. What happens when n equals 3? Well, when n equals 3, we're dealing with a pentagon. And we have a picture here, one of them. So we have to draw two diagonals that don't cross. Here's one choice. Both diagonals contain 1. Are there others? Yeah, you can do the same thing at any other point. So I do it here at 2. Both diagonals contain 2. You can do, one is here, 2, 3, 4, 5. And then one more here. 1, 2, 3, 4, 5. Both diagonals contain 4. And I'll draw the last one over here. 1, 2, 3, 4, 5. Both diagonals contain 5. And this will give us that C3 is 5. Okay. All right. What about higher values? So let's keep track of them somewhere. So again, let me write it here so that we remember Cn, the number of regular. It doesn't have to be regular, but it's a bit simpler to think about. Of a regular n plus 1 to gone by n minus 1 non-crossing diagonals. So thus far we have n is here, Cn is here, and we calculated for 1, 2, 3. So we got 1 here because we had a triangle. Here it was 2 because we had a square, and here was 5. Well, what will be when n equals 4? So when n equals 4, let's get ready to draw. So when n equals 4, we're dealing with hexagons. So let's say I have 1, 2, 3, 4, 5, 6, and I need to draw 3 diagonals such that they do not cross. So as before, the easiest one could be the ones that contain the same point. So in this case, I draw this one, and you kind of get the picture of how it's going to work. 1, 2, 3, 4, 5, 6. You can draw this one, and so on. So you're going to get 6 of this type of triangulation. So I won't draw all of them. Okay. Are there others? Well, let's see. 1, 2, 3, 4, 5, 6. Well, we can try to draw it this way. 1. You have this letter N inside formed by the diagonals. And I can, essentially what I did in the first row, I started with one of these triangulations and I kind of rotated it at each step, I can do something similar here. So I can, the next triangulation of this sort would be this one. If I rotate it clockwise by 60 degrees. And then 1, 2, 3, 4, 5, 6. And then if we continue this way, we get this triangulation. Then if we do it one more time, you're gonna see that we're gonna end up back to the one that we started. If we rotate the one on the right here one more time, clockwise by 60 degrees, it's gonna give us the one here. Okay, so we got 3 more here. Well, obviously, you can see that you can do something similar to the following triangulation. 1, 2, 3, 4, 5, 6. You go this way. I guess it's a Cyrillic letter I, and then you can do the same rotation. 1, 2, 3, 4, 5, 6, and let me see how this goes. This way. And another one. 1, 2, 3, 4, 5, 6. Goes this way. And again, if you rotate it one more time, you go back to where you started. So we have 3 more triangulations here. So 3 triangulations, 3 triangulations. Are there any others? And there are 2 more. Pattern inside the inside, and one more kind of similar triangle here. So you have 2 triangulations. So you can check, I guess, by exhaustive analysis and so on, that these are all the triangulations and of a hexagon, and there are 14 of them. So we get 14. Now, you probably are convinced now that we may not want to try this argument for other values, 6, 5, 6, 7, 8, 9, and so on. You know, if you have a heptagon for n equals 7, for when n equals 5, we're looking at 5 plus 2 gon, a heptagon. That might be a bit too much. So let's try to look for a recurrence relation for these parameters instead. And here's what's going to happen. So let's say we have an n plus 3 gon. So I put here the 1 at the bottom. The other one is n plus 3, and I go here, I have the 2, the 3, 4. On this side, you come with n plus 2, come back with n plus 1, and so on. Now, one thing that I'm not going to prove, but I invite you to figure it out, is that every, because we're using, so in this case, I'm going to have n diagonals and non-crossing diagonals. The edge, this side, 1 n plus 3, is going to be containing exactly one triangle of this triangulation. So there's going to be some node here. Let me call it k plus 2, where this edge 1 n plus 3 is contained. So there's this triangle here. So if you look back at the previous example, you see it here when n and 6 is my n plus 3 here. You see that this edge is contained in this triangle here. This edge is contained in this triangle here. This is always the case. If I have it here, the edge 1, 6 is contained in this triangle. So that's always the case. So it's not very difficult to prove. So this k, how large can this k be? Well, k plus 2, this point here, can be anything from 2 all the way to n plus 2. So k plus 2 is greater or equal to 2 and is less than or equal to n plus 2. So that makes it that k is between 0 and n. Okay, so we keep that in mind here. So k can start from here. K plus 2 can start from here, here, all the way back over here. Okay, so there are n plus 1 possible values that k or k plus 2 can take. All right, and now, so what are we trying to count? We are trying to count, because we are in this n plus 3 gon, Cn plus 1 is the number of triangulations of this n plus 3 gon by n non-crossing diagonals. That's his definition. And so for every k, for every such k, and for, whenever we have this this triangle that contains 1, n plus 3, and k plus 2, we're gonna get a triangulation of this n plus 3 gon by combining a triangulation from here of this. This is a k plus 2 gon, and we're gonna combine it with a triangulation from here, which is a n minus k plus 2 gon. So here again, I guess the definition that we want a regular is not necessary. Just put a convex. Any convex would work. A convex n plus 1 gon, and the same thing here. Okay. So we're gonna get the number of triangulations of this n plus 3 gon are gonna be obtained by combining this a triangulation of this k plus 2 gon, the purple one, with the dark blue one. Now, how many triangulations are we gonna have of each side? Well, the number of triangulations of a k plus 2 gon is gonna be ck. And any triangulation that we have here in the purple can be matched with any triangulation that we have on the right in dark blue. So it's going to be ck times cn minus k. Again, the c, the ck counts for k plus 2. The cn minus k counts the number of triangulation of n minus k plus 2. So that's why we have a product here, because any triangulations on the purple can be paired up with any triangulation in the blue. And then as this k takes different values, you get different triangulations, so you have to sum them up. So this is going to be sum up from k equals 0 all the way to n. So the formula that we get is Cn plus 1 equals the sum from k equals 0 to n of ck cn minus k. And it's a different type of recurrence relation than we've seen until now. So it's definitely not linear. So we have this recurrence relation. Okay. All right. So now, how can we use it to say something more? Well, you can use it to, first of all, to fill up these details here, and I'll leave it to you to figure out some of these numbers. I'll just tell you that the 145, the one that we avoided doing by hand, is actually 42. So that's actually a good thing. But yeah, I figure out these numbers, these small values. You can find all these small values if you have any sequence that maybe you know, or and you want to find out more about it, or maybe you don't know, you have some sequence, you know, some initial values like this, and you don't know anything about it, just go to oais.org. This is the online encyclopedia of integer sequences. So it's created by a brilliant person named Neil Sloan, and it contains so much useful information. So you can look it up there. So if you go to this webpage and you look for, you can just type in Catalan numbers, and we'll give you a lot of information about it. Or you can type the sequence 1, 2, 5, 14, and the website will give back to you all the known sequences that from the database that start with those numbers. Okay, so now coming back to our problem, so you can calculate Cn using this recurrence relation, but how can we actually get a handle, say something about the value of Cn? I mean, we can calculate it numerically for recursively by this formula, but how can we figure out a formula for it? So here's how we're going to use generating functions. So to the sequence Cn as before, Cn and greater or equal to 0, we associate its generating function. So it's f of t summation n is 0 to infinity Cn t to the n. Okay. Now, what do I need to use? I need to use this relation somehow. Okay. So Cn plus 1 on the right, that's gonna relate to this formula somehow. And then ck times Cn minus k, it kind of gives me an idea about, you've seen this type of summation in the product of formal power series. So here's what we're gonna do. You can start from this relation Cn plus 1, and so we can write that because this relation is true for every n greater or equal to 0, we can write summation for n greater or equal to n is 0 to infinity of Cn plus 1 times t to the n. It's the same thing as summation from n equals 0 to infinity of summation from k equals 0 to n of ck Cn minus k t to the n. Okay. Now we're going to work to expand each of these sides. The one on the right is actually simpler here because this is exactly f square of t by the rules of how you multiply two formal power series. The one on the other side, what is it going to be? Well, let's look at it a little bit more. So it's going to be n equals 0, I get C1, and then I get C2 times t to the power 1 plus C3 times t squared, and so on. So how can I get my hands on that? Well, let's rewrite f of t. So let's write it here. F of t was C0 plus C1t plus C2t squared plus C3t cubed, and so on. So you see, there is a bit of a similarity here to some parts of this sum, this one here. So what was C0? Do you remember? C0, we define C0 anywhere. I guess we can take C0 to be 1 because that was the number of triangulations of a two-gon, and a two-gon is a segment. So we can take C0 to be 1. And so we're gonna get 1 here, plus I can take t as a common factor here, and what do I get? I get C1 plus C2t plus C3t squared plus dot dot dot, which is exactly this part that I had from here. And so with this in mind, I can basically figure out that what I was trying to find out, the expression on the right, this one equals f of t minus 1 divided by t. It's from this equation from here that you find it. You subtract a 1, move a 1 to the left, and then you divide it by t. Okay. So in the end, what did we end up with? Well, I ended up with f of t minus 1 divided by t equals f squared t. So I will write it here. F of t minus 1 divided by t equals f squared t. So that's the equation that we found out. It's satisfied by the generating function for the Catalan number. So let's rewrite it here. So f of t minus 1 over t equals f squared t. And now we can write this as an equivalent form as a quadratic equation. So we move the t to the right, tf squared t, and we move everything to one side, minus ft plus 1 equals 0. So this is a quadratic equation in f of t, and if you solve it, you're going to get two solutions. F of t could be 1 plus or minus square root of 1 minus 4t divided by 2t. And now, how do we deal with with the square root and all that? Well, again, from the binomial formula, we have that square root of 1 minus 4t. It's the same thing as 1 minus 4t to the power 1/2. And this can be expanded as an infinite sum for n is 0 to infinity of 1/2 choose n minus 4t to the power n. And you can expand a few terms. So something to 0 is gonna be 1. So the first term is gonna be 1, and then you can get minus 2t minus 2t squared. This requires some calculations, but you can do it using the formulas for the binomial coefficient and so on. So now what we have to choose is from these two formulas, there are two possible choices for f of t. Can it be 1 plus square root of 1 minus 4t divided by 2t, or is it 1 minus this one, 2t? Well, if you were to be plus, then what do you get? On the top, when you expand this calculation, you're going to get the 1 from here is going to match with the 1 from here. So when you divide by 2t, you're going to get 1 over t. Then you get the minus 2t divided by 2t is 1, minus t2 squared, minus 5t cubed, and so on, minus. Now, this cannot appear in a formal power series because its power is t to the minus 1. So it's definitely not this formula that f of t is not, this one is not the correct formula for f of t. So therefore, it has to be this one. So we have actually that f of t equals 1 minus square root of 1 minus 4t divided by 2t. This is actually another formula for the generating function of the Catalan number. And now, from here, I'm a bit out of time now. So from this formula, you can write over 2t. You can write this as using the binomial formula. So this is going to be summation n equals 0 to infinity, something of the form minus 1/2 to the n plus 1 minus 4 to the n plus 1 divided by 2 t to the n. And it will give us some very weird looking formula like this. But this can be simplified, and we'll do it next time to the following very nice formula. Cn is going to be 2n choose n divided by n plus 1. But we'll do all of this next time. Thank you.